Hi team, let's take a look at one of these more sophisticated models, although I'm going to break this into two videos. I'm going to do kind of a part A video, part B video with the valence bond method, because the valence bond method is kind of simplistic. It's sort of what we've been talking about. I think qualitatively it's good to think about, but doesn't quite match experiments, so we're going to have to modify it a little bit with what's called hybridization, and then it kind of matches experiments. So we had to fudge it a little bit until molecular orbital theory came along later. But in essence, what's the valence bond method? All right, so we've got two atoms. They're going to approach each other, and we saw that from the model. You see, you got all those different attractive and repulsive forces between electrons and neutrons and nuclei, right? And we saw the energy. We want to go to that lowest energy state. Let's think about this overlap that's going on. So the atomic orbital of atom number 1 and the atomic orbital of atom number 2 are going to start to overlap because the nuclei are these tiny little centers. So it's the electron clouds, the electron density regions that overlap that are in the orbitals, which are just wave functions from quantum mechanics, right? So they're going to overlap first. For example, you can look at two hydrogen atoms to make it really simple. You got the little tiny nuclei and you got the 1s, right, orbital. So the orbitals are, especially if you've got more complicated atoms with a lot more electrons, you're going to have valence electrons and core electrons. So it's the valence electrons, the valence orbitals that actually overlap, right? So the atomic, you could put valence atomic orbitals if you want to. They penetrate into each other, right? We call that overlapping. We say they overlap, but they're penetrating each other. Now, really, remember their wave functions. So technically, this is how most people talk about valence bond method, but technically, the wave functions are combining, right? And if they're in, remember constructive and destructive interference, if we have two waves coming and they're in phase, boom! I talked about my grandma wiping me out inner tubing and stuff. She'd get the waves coming, little 1 foot waves that combine in phase, and now you got a 2 foot wave and she slams you into that and you dislocate your shoulders. Yay, grandma! Right? So if these atomic orbitals are in phase, if those wave functions are in phase, they will constructively overlap. And if they do that, that creates a very high electron density region in between. See where I did the overlap there? You get a really high electron density charge region in between the two nuclei. And that high electron density region is attracting this nuclei of atom number 1 and that nuclei of atom number 2. And that's the attractive force that holds them together. Of course, you'll have an internuclear distance at the lowest point of that curve, right? So you've got the bond length and whatever that bond energy is. So that attractive force, due to that constructive interference of the two electron waves, i.e. the atomic orbitals overlapping, that's your bond. And if you move up the levels, become a chemistry major, maybe get a master's, maybe get a PhD, your whole viewpoint of bonding is probably going to change. All right. You'll see as you go higher and higher that we oversimplify things. You have intro chem, then general chem, then organic, and we open up the ugly doors or have you jump down the rabbit holes into the chemical wonderland. But sometimes we don't want to open those doors at the lower level because that conceptually is just too challenging. So I got some friends that work UC High that do bonding models that I'll go and listen to them talk, and I just, wow, wow, you just don't think about it. So we're going to keep it fairly simple here. Let's look at this and more. Let's do like an example of this, show you kind of what it looks like and how it works okay, but doesn't quite match some of the experimental data. All right, we saw hydrogen. That was pretty simplistic. Let's take something a little wee bit more advanced. Let's do something like ammonia. So if you remember with Lewis structures and Vesper structures, let's compare and contrast these real quick. So let's take the Vesper model. And if you want to pause this, go ahead and do the Lewis structure. And then from that, draw the Vesper structure for me for ammonia and predict the bond angles for me. Do that real quick. And then what we'll do is we'll do the same thing using the ideas of the valence bond method and show you kind of what the bond angles would predict there. And I'll show you that they're close, right? Depending on the molecule, some are really close, some aren't so close. But I'll show you what I'll point out a couple of flaws in the valence bond method and why we have to introduce this concept called hybridization, which we'll do in the next video. And that helps fine-tune this particular idea, the valence bond method, to help match what we measure in experiment. Because a good theory needs to match the experimental data. Oh, all right. So let's go. So hopefully you can pause this and do it yourself. Let's do the Vesper structure. I'm going to skip the Lewis structure. All right. Hopefully you figure if you do your 6n plus 2 minus valence electrons, you get 0. So there's no double bonds, no electron deficient species, no expanded octets, anything like that. So let's draw that nitrogen in the center. You're going to have 3 single bonds and a lone pair once you do it. So I like to put the lone pair up on top. You got four electron groups, so that's a tetrahedron. So I'll kind of draw the tetrahedron like this. Right, so you got the dash wedge structure. These are in the same plane. This is coming out at you. Have you forgotten all this? I like to keep my hydrogens here at the base of this pyramid and then put my lone pair here. You could draw an orbital like that or just leave the lone pair like that. I don't care. However you want to do it. But the resulting structure is trigonal pyramid, right? And what was the bond angle for the trigonal pyramid? Remember? Now, tetrahedral is 109.5, but that lone pair takes up extra space and pushes them a little closer. And I kind of said for every lone pair, maybe subtract about 2.5 degrees, so go from 109.5 to about 107, give or take. So this bond angle right here is about 107 degrees as far as our bond angle. Give or take a few tenths of a degree here and there, but you get a rough idea. So let's do the same thing, but let's look at it from the valence bond method and see what we get. I'll explain it and see if you can do it on your own. So in the valence bond method, what we're going to do is we're going to take that central atom, nitrogen, draw its valence orbitals. Right, so if you look at nitrogen, right, let's get the periodic table. Haha, my periodic table's getting all beat up. Nitrogen's in the n equals 2 level. So here's n equals 1, n equals 2. There's your nitrogen right there. So we're going to take that n equals 2, right, and the outermost one would be the 2p. So draw the 2px, the 2py. So draw nitrogen with a 2px, 2py, and 2pz orbitals for me. Do that. And then bring in the hydrogen, which is the 1s, right? That's all it's got. And overlap the hydrogens, the 3 hydrogens, with the 3p orbitals. And then see what bond angle you predict from that. I'm going to pause this, draw it, and let's see if what you draw matches what I draw. All right, so it should look something like this. You might have put the hydrogens on, different sides of the p orbitals, but so here's my nitrogen. Here's my 2p. Now you don't quite have to draw. Remember, there's a positive and a negative lobe. We don't really know which one's positive or negative, but not critical at this point, right? So we've got a p orbital with its 2 lobes, right, in the z direction. We've got the p orbital with its 2 lobes in the x direction, the 2px, and then we got the 2 lobes of the 2py, which is really supposed to be coming out at your face, right? So they're sticking straight out, but how do you draw that on a 2-dimensional board? All right, so we kind of angle it out, so it's a little harder to see, but if we did a model, I'd have the x going this way, the 2 lobes, the z going this way, and then it'd be like a clown nose for the p, coming at you and coming away from you. Hard to draw, right? But let's take a look at that, and then we'll take, you could call the purple positive and the black negative. Whatever, doesn't really matter. So we'll bring the hydrogen atoms in, and their 1s orbital is going to penetrate or overlap or constructively interfere with, when the wave functions overlap, the p orbitals, right? I picked all of the purple ones. You could have done the black ones, doesn't matter. And you see the red regions, that's where you get the constructive interference. You get a high electron density right in between those, and that's the attractive force between the nucleus of the hydrogen and the nucleus of the nitrogen. That's the bond that holds them together, the attractive force. But thinking about the p orbitals, what are the bond angles here, right? So let's look at it's clearest here. It's kind of hard to see right here. Remember, this is coming out at your face, and so it's in this plane here. It's hard to see, but we can see this right here between the z and the x planes, right? So between here and here, what's the angle between the 2px pointing this way and the 2pz pointing that way? What's that angle? Well, it's 90 degrees, right? That would be true if we did the y with the x. Do you see that? That would also be a 90-degree angle. So all of this would predict a 90-degree bond angle. Well, Vesper predicts a 107. In reality, it is around 107. So, you know, close, but not good enough for us. So there's some flaws to the valence-bond method. We like the idea, right? The wave functions of those valence orbital electrons overlapping. So we like the idea, but something's off a little bit here. So let's talk about some of the flaws of this and how we might remedy that. All right, so real quick, I want you to look at the thinking of this. And when we get to hybridization in the next video, hopefully that will help make sense. A couple of flaws in the valence-bond method. One, it's using a localized electron concept. All right, we're not even looking at the core electrons and stuff like that, only the valence ones. So what's happening with the core? So we are pretty much just keeping the core electrons and lone pairs. Remember, we didn't even look at the lone pair for the ammonia. Where did that go? Right? We didn't even look at it. We looked at the overlapping the hydrogens. We didn't stick the lone pair anywhere. Oh, that's a problem, right? So we just assume lone pairs and core electrons just stay in the same atomic orbitals as the separated atoms, right? There's absolutely no change in there. Yeah, is that a safe assumption? And we assume there's no change in the orbitals themselves. So I've got atom number 1, atom number 2 with their atomic orbitals, sp, d, and f. And as they come together and overlap, we're assuming they don't change at all. They maintain their exact original atomic shapes and energies and all that kind of stuff, right? How do we know that? How do we not know something happens when they're coming together and it's going from separated atoms to a molecule, that there's not an actual change when they come together? They don't interact with each other and cause a mutual change in each other. So we're going to remedy this atomic orbital, unchanged atomic orbital perception of the valence-bond method. So we're going to fine-tune it, and we're going to include a concept called hybridization. So we're going to keep the valence-bond method idea, but we're just going to allow a change in the orbital, the atomic orbitals, and we're going to allow what's called hybridization and use hybrid orbitals rather than atomic orbitals. That'll be the first fix for that. So it's just kind of like a specialized valence-bond method. And then we'll actually look at molecular orbital theory like we talked about, right? The two extra more sophisticated models where the atomic orbitals don't even exist anymore. They morph into molecular orbitals. Hey, let's get into it and let's do some hybridization in the next video.